So the idea of arc length is going to be this. Let's say we have some curve. And what we're going to try to do is approximate the length of this curve. Well, let's pick some destinations, actually. Let's say we do this. Let's not start at the y-axis. Let's go from A to B. So we want to approximate the arc length of this curve from A to B. And what we can do is we can do this using line segments. So we can approximate the curve f of x using line segments. So the idea here, if we have more and more smaller segments, we're going to have a better approximation of f of x. Now let's take a look at one of these segments. Sort of zoom in. So here's one of these segments. And what we can do, we can analyze this like it's the hypotenuse of a right triangle. So we're going to call this the height of this triangle, delta yk. And we're going to call the width delta xk. And the length of this part of the curve, we're going to call the line segment here, approximating that length, lk. Now, using the Pythagorean theorem, this says this line segment is approximated by this, or this line segment is approximating our curve, and the line segment itself, using the Pythagorean theorem, is delta x k squared plus delta yk squared. So any questions about that so far? Because now we're going to pull out a little trick. The trick's going to be this. It's the mean value theorem. And we've seen this before. And what this is going to say is this. Y at xk minus y, or let's stay with f. Let's do f at xk minus f at xk minus 1 over xk minus xk minus 1. Well, this is going to be equal to the derivative of f at some ck where ck is in the closed interval xk minus 1 xk. So our friend the mean value theorem comes back. Now another way of saying this, f at xk minus f xk minus 1 xk minus xk minus 1. Well, we could just call this yk, and this other f of xk minus 1, we'll call that yk minus 1 over xk minus xk minus 1. Or what we're getting is the height of our triangle and the base of our triangle. So delta yk, delta xk, and according to the mean value theorem, this will be equal to f prime at ck. Any questions about that? So we're sort of doing some tricks here, but there's method to the madness. You have delta yk and you have delta xk equal to f prime c sub k. So what we're going to do, we're going to solve for y. And this means we're solving for delta y. So delta yk equals f prime ck times delta xk. So now we're going to go back to LK. Now recall that this was delta xk squared plus delta yk squared. Ooh, just a little bit. So now we can rewrite this delta xk squared plus, and we'll do the substitution, f prime ck delta xk squared. And we'll do some simplification here. And what we're going to do is factor out delta xk squared. Like so. And so we're going to break up our square root. Like so. So we're going to have the square root of something squared, and delta xk is always going to be positive. So what this is going to do, it's going to help set us up ultimately for an integral. So any questions so far? All right. Oh, okay. I think something happened. It dropped off for some reason. Oh, okay, well, I'm going to continue on. Yeah, did I disappear for a moment?
Yes, you did.
Yes.
Oh, I'm not sure what happened. I think my Teams crashed, but it's back up and running, so I'm going to continue on. So we take the square root of delta xk squared, we're going to get delta x k. And this is equal to lk. So the idea is going to be this. This is the length of that line segment. It was that hypotenuse that was approximating the curve. And what we've done is we have a bunch of these line segments. So this could be L1, this could be L2, this could be our L sub k, and so on. So if we add up these segments, we're going to get an approximation of the length of our curve. And so that's going to be our approximation. Now, again, if we make these segments smaller and we have more of them, we're going to get a better approximation. So ultimately what we're going to do is we'll take the limit as n goes to infinity sum of lk, which will be the limit as n goes to infinity, 1 plus, we have our, oh, f prime, I apologize, but this is f prime. F prime, don't forget that prime on there. F prime ck squared delta xk. And again, just in your notes, don't forget that prime. That's going to be massively important. And what this will become is the integral from a to b of the square root 1 plus f prime of x. Again, we don't want to forget that prime squared dx. So this is what we're going to use to find the length of a curve between A and B. And sometimes what we'll do, you might see it written like this. You'll sometimes see it in that form. So questions about that? All right. So let's take a look at an example. Let's say we have this. Let's say we have f of x equal to x squared over 4. Oh, I'm sorry, I'm getting ahead of myself here. X cubed over 12 plus 1 over x. And we'll take x between 1 and 4. And so we want to find the length of f of x between these two locations on the x-axis. So going to our formula, what we're going to need is f prime. If you calculate f prime, you'll get x squared over 4 minus 1 over x squared. And what we can do, we can compute this piecewise. If we take a look at our formula, we need this. And if we simplify this down, we would FOIL this, and what we would get would be x to the 4th over 16 minus 1/2 plus 1 over x to the 4th. I'm going to admit, from an algebra point of view, this could be kind of a tricky one, because we're going to have to try to integrate this. So here's a little trick that could help. It's called x to the 4th over 16. Let's call that x squared over 4 squared. What we're going to try to do is we want to try to rewrite this. So we're taking the square root of a quantity squared. So this is something that kind of a little trick to look for. And what we could try, let's see here. I'm just thinking of a technique that could help. Well, you could try this. Now they give you the result in the textbook, but what you could do, I'm going to go back a bit. Let's go back to this right here. I'm going to factor out 1 over 16. See if that helps. And trying that, we can call this x squared squared plus 8 plus, let's go 4. Oh, we'll just keep it with x squared. See if this helps. And if we let, I'm going to call v, let v equal x squared, then we'll get 1 over 16 v squared plus 8 plus 16 over v squared. It's helping it all. Well, there's even a better way of doing that. I apologize. What you could do, and I'm sorry, I'm kind of mucking about, but I want to try to explore how you come up with the answer, the algebra that the book gave you. And so what you could do, let's factor a little more. Let's factor out 1 over x to the 4th. This would become x to the 8 plus 8 x to the 4th plus 16. We could do something like this. So we factored out the 1 over 16. We're now factoring out the 1 over x to the 4th. So basically we started with this. So if we factor out 1 over 16, and then we're going to factor out 1 over x to the 4th, we're going to get this. And then with this, what we can do, we let our v equal x to the 4th. And so we'll get 1 over 16v times, this will be v squared plus 8v plus 16. And then what we can do, one over 16v, this will become v plus 4 squared. So it took a few experiments to see where this was going. But then we take the original one, factor out 1 over 16, factor out 1 over x to the 4th. We're going to get this. Let v be x to the 4th. We're going to get this, which lets us get that. Now we can take the square root. We'll have 1 over 4 square root v times v plus 4. Replace our v's, we'll have 1 over 4 square root x to the 4th times x to the 4th plus 4. Pardon me. Oh, I'm sorry. Forgot to bring that up. So we get 1 over 4x squared times x to the 4th plus 4. And if we distribute, we'll get x squared over 4 plus 1 over x squared. Whew. So I had to play around with some algebra there, but there we go. We're almost ready for our integral. So any questions? I know that's sort of a journey down the rabbit hole of algebra, but we wanted to wrestle with that one a little bit. All right. So let's go back to our curve problem. If I'm going too fast, let me know. I'll give you another little bit of time to write down that. All right. What we figured out, we wanted to get rid of that square root. That's why we went to all this trouble. So what we ended up discovering was that the square root of our x to the fourth over 16 plus 1/2 plus 1 over x to the fourth, that's going to come out to x squared over 4 plus 1/2. And rightly, this would usually be an absolute value. In this case, we've got an x squared. We got x to the fourth, x to the fourth. If we're taking the square root of that, this is always going to be positive. Also, x is between 1 and 4. So our x's are going to be positive. Everything. Oh, yeah, yes.
Sorry to interrupt you again. Did anyone else's screen go blank?
Oh, it is blank. I'm sorry. Let's wait.
Yeah, I'm sorry. I don't know if it's my connection because my connection has been bad today.
It's not your connection. Okay, there it is.
Thank you, sir.
No problem. No problem. Yeah, yeah, this camera, I think, is coming to the end. All right. So that's all that we did. We wanted to get rid of this square root. Awesome. The x's we're choosing x between 1 and 4. So our x's are going to be positive. What we're doing with the x's, we're always going to have positives. So the square root of this, it's going to come out positive. So our length, which is our integral from a to b of the square root 1 plus f prime ck, and squeeze in a square. Well, that's now going to become the integral from 1 to 4. And we calculated what the square root turned out to be. It's x squared over 4 plus 1/2. And if we hammer that out, what we're going to get is an answer of 6. Questions about that? All right. So,
how did it change from 1 over x squared to 1/2?
Let me see.
From the answer that you circled on the last screen?
Oh, let me see. So what happens is we had 1 over 4 square root v times, let's see, and then we had v plus 4. Let's see, let me double check. Plus 4, so we're going to get 1 over, we're going to get v over 4 square root v plus 4 over 4 square root v. Oh, I see what you're saying. Oh, I'm sorry, you're right. Ooh, it is 1 over x squared. I apologize. I wrote that down wrong. You're correct. Yeah, I'm not seeing where I got that 1/2. I apologize. That is 1 over x squared. You're correct. Thank you. Thank you.
Okay, thank you.
Yeah, sorry about that. That's gotta be confusing. Any other questions or observations? Prone to miss a term or terms. All right. So that's the arc length formula. Now, there's a couple things with this to look at. One is you can do this formula as dy dx. So you can have y as a function of x, or you can solve this so x is a function of y. You could do this, and then you can integrate along the y-axis instead of the x-axis. So what that's going to mean is your length will be an integral from c to d of the square root 1 plus g prime of y squared dy, or the integral from c to d 1 plus dx dy squared dy. And the example we're going to look at, it's an interesting one because it shows why you might want to switch from this to this. And it's kind of a neat little problem. So any questions about that before we jump into the example? All right. So let's say we're going to do this. We want to find the length of y is x over 2 to the 3/2, or 2/3, from x is 0 to x is 2. Now, where this becomes a problem is when we try to put the formula together. So if we take a look at our formula, the integral from a to b, or for us it'll be 0 to 2, 1 plus f prime of x squared dx. Now, this is where we run into a problem. If we compute f prime of x, what we're going to get is 1/3 2 over x to the 1/3. Now we're integrating this from 0 to 2. The problem is f prime of x is not defined at x equals 0. So how do we use this in our formula if it doesn't have a value at x is 0? So this is where we might try looking at this. Instead of integrating along the x-axis, we could integrate along the y-axis. So let's try that. Let's solve this thing, not as a function of x, as a function of y. Now, if we do that, we start with it as a function of x. And if we solve for x, so we take 3/2, the power of 3/2 on each side, and multiply both sides by 2. We're going to get that as our function in terms of y. Now, any questions about that, especially this step? Any questions about going from here to here? What I basically did is applied the power of 3/2 to each side. You use the exponent of an exponent means you multiply. So 2/3 times 3/2, that's just going to be 1. That's what gives us this expression here. And then you have y to the 3/2. So now what we're going to do, now that we have our function in terms of y, if we take the derivative dx dy, which is our g prime of y, what we'll get is 3 y to the 1/2. Now, are we still okay? Is this actually an improvement on things? Well, we got to look at our bounds of integration. For x, our bounds were 0 to 2. So now I got to figure out what the bounds would be for y. Now to do that, we go back to the original equation. Y is x over 2 to 2/3. And if we go with 0, well, this would be 0 over 2 to 2/3, which is actually going to turn out to be 0. So for x equals 0, then y equals 0. Oh, hang on. Now let's take a look at another one. Now we were going from x is 0 to x is 2. So now we take a look at 2 over 2 to the 2/3, and that's going to come out to 1. So for x equals 2, then y is equal to 1. So what this is going to imply, if we're integrating along y, we'll go from y is 0 to y is 1. Now, thinking about this, our original function, or the one in terms of y, I should say, we want to see if there are going to be any discontinuities. So we have for y, 0 to 1, we're dealing with this function, x equals 2y to the 3/2. And if we were to take a look at this, there are no discontinuities. We can put a 0 in for y, and that's going to be fine. And we took, oh, I'm sorry. Let me go a little bit farther. We needed to look at x prime, and that was 3y to the 1/2, because it was the derivative of the function that we're using in our formula. Well, same thing though. Again, you're taking, basically this is 3 times the square root of y, and you can take the square root of numbers between 0 and 1, including 0 and 1. So that's perfectly fine. So now our formula is going to be okay. So we take the integral c to d square root of 1 plus g prime of y squared dy. That'll be the integral from 0 to 1 square root 1 plus 3 y to the 1/2 squared dy. And this will be the integral from 0 to 1 square root 1 plus 9y dy. And I'll go through the integral on this one. It's going to be a u substitution. So we can let u equal 1 plus 9y du dy will equal 9, or du is 9 dy, or 1/9 du equals dy. So that's how we can replace dy. This is what we're going to replace with u. As for our limits of integration, for y equals 1, u will be 1 plus 9 times 1, or 10. For y equals 0, u will be 1 plus 9 times 0, or 1. So any questions about that? All right. So this puts our L 0 to 1 square root 1 plus 9y dy. This will become the integral from 1 to 10 square root of u 1/9 du. So the 1/9 will just pass through. Integral u to the 1/2, that's what square root u is. We'll get u, it would be 2/3 u to the 3/2 from 1 to 10, or 2/27 u to the 3/2 from 1 to 10. Ten to the 3/2 minus 2/27, 1 to the 3/2, or 2/27, 10 to the 3/2 minus 2/27. And approximately, I'm just going to check this on the machine here. Well, we can keep it exact. Factor out 2/27, and we can call 10 to the 3/2 10 cubed to the 1/2 minus 1. Or 2/27 times 1,000 to the 1/2 minus 1. And that's going to be 2/27. I'm just going to kind of do a blast from the past with some arithmetic here. This is really the square root of 10 times 10 times 10 minus 1. And we can pull out a couple of these 10s here. We'll get 10 square root 10 minus 1. So any questions about that? All right. So one more thing to talk about in this section. And this is going to be the differential formula. For arc length. So what we're looking at is something like this. We want an arc length from starting point A to some chosen X. So what it is, we want to come up with a formula that we could use for a particular curve. So we can have something like, say this. And here's A. And we want to find the curve, say the length from here to here, or maybe here to here, or maybe we want to find it from here to here. Is there a formula we can come up with to find the arc length from some starting point A to some x that we just sort of choose at random that's bigger than A? There's something like that we can do. Well, there is, and this is how we set it up. We'll call it S of x from A to x. And then we're going to use the variable t. T is what's called a dummy variable. It just allows us to perform the integration. So this is the formula we would use. So any questions about that? So what we're going to do next is we're going to apply the fundamental theorem of calculus. And the one that we're going to apply is where we're going to be able to take the derivative of this. And according to the fundamental theorem of calculus, when we take this derivative with respect to x, even though this is in terms of t, we take it with respect to x, what we're going to get is ds dx. And again, derivatives and integrals act like inverses of each other. So we're going to get what was inside the integral. Except this time, according to the fundamental theorem of calculus, instead of being in terms of t, it's going to be in terms of x. And again, that's that fundamental theorem of calculus that allows us to do this. And we could rewrite this as 1 plus dy dx squared. So why are we interested in this? Why do this? Well, S is the entire length between A and some point X. ds is what we're going to call a differential arc length. Now, we've talked about differential x, this infinitesimally small distance on the x-axis. We've talked about the differential y, or dy, this infinitesimally small distance on the y-axis. Now we're talking about ds, an infinitesimally small distance on the curve. In fact, I'm going to be careful with using distance here. I'm going to say differential. So we've talked about differentials, and we treat them as tiny distances, but we talk about them on the x-axis, on the y-axis. Now we've got one located someplace else for the first time. Now we've got one located on the curve itself. And so what we're going to find, and we've talked a little bit about this in that section on differentials. So the differential length on a curve, we can solve for ds. We get that ds is the square root of 1 plus dy dx squared dx. So again, this is going back to that section on differentials. And we can simplify this a little more. We can say ds is the square root of 1 plus dy dx. This is squared. I'll better put brackets around this. Dx squared. In fact, I'll just put parentheses around this one. As if we had taken the square root of this and it popped out like that. And if we were to distribute this through, we're going to get this. So this is what our ds becomes. And so what we're going to say is that the length, which was the integral from a to b of 1 plus dy dx squared dx, which is exactly what we had up here. Well, this can be rewritten as the integral from a to b of ds. So the length is the integral of the differential length. That's what that's saying. And this is going to come back later. We'll see this again in Calculus 3. So any questions about that? All right. So we're going to jump into section 6.4. And 6.4 is an application of the differential here. Now I'm thinking just for the sake of time, I'm going to skip the derivation just because we're down to about 34 minutes. So I'm going to give you kind of an idea of how this works. But this is surface areas or areas of surfaces that are generated by revolutions. And the idea is going to be this. Here's our x-axis. Here's our L. And what we're going to do, we're going to revolve this around the x-axis. Like so. And what we're going to do with L, again, we're going to say that L I'll do a little bit of a derivation here just to give some context to this. But again, L is going to still be delta x k squared plus delta y k squared. Same as before. And again, we could think of this for L, if this is L, delta xk, delta yk. And here this would be, say, xk. Here would be xk minus 1. And f of xk equals y sub k f of xk minus 1 is yk minus 1. So the difference in x's and difference in y's, that's giving us our delta xk and our delta yk. Now, the idea is going to be this. So I'll go through some of the derivation. Let y star equal the average between yk and yk minus 1. So what we can do, we can describe the surface area. This is called a frustum. And we can describe the surface area of this frustum and we're talking about the wrapper on this, not the ends, not the top or the base, but just the wrapper is this would be L along here, is L, and then you have this. The circumference of this average value of y, 2 pi y star. So this could be where y star is coming around. So this would be the yk coming around. This would be yk minus 1 going around. And this would be like y star going around. So the area could be described of this wrapper on this frustum could be described using this. So any questions about that? All right. If I'm going too fast, please let me know. So what this means for one of these frustums, A sub k, the area is going to be 2 pi y star times L sub k. Or 2 pi, and then we'll break y star up. It's the average of these y values. So f of xk minus 1 plus f of xk over 2, because there's 2 of them. And then L, square root of x, k squared plus, sorry, not, delta yk squared. And we're going to get some cancellation. We'll get pi f xk minus 1 plus f xk. Then we have our square root. So we're going to do, and I'm going to kind of take a shortcut here. Again, we're going to use the mean value theorem. And what that let us do is we could say delta yk for some ck we can rewrite it like that. We're going to make this substitution. Then as these intervals, xk minus 1, xk, containing ck get smaller, what's going to happen is this. If we want to find the surface area, that's a whole bunch of these frustrums. We have a sum of these frustrums. And what that lets us do, get a picture of what a sum of these is going to look like. So we have our curve, A to B. In fact, let me draw this a little differently. I apologize. A little smaller. What we're going to do is we're not just going to take just a line segment L and revolve it. This is an A and this is a B. What we're going to have is a bunch of these that we're going to revolve. And when we do that, we're going to get a bunch. Pardon my drawing skills here. What we're going to get are a bunch of these shapes. Going to give us something like this. So remember what we've been doing. We calculated the area of the wrapper on one of these frustrums. So if we sum these areas, and these are all areas of the wrappers of each of these frustrums, the sum of these frustrums give the surface area of the object. So what this is going to, now any questions about that? So what we're going to get, now we've used our mean value theorem. So that means we've used the same trick that we had used to get the formula for the length of a curve. So now we have this. And if we use the mean value theorem, replace delta yk with f prime ck delta x, we can simplify and get that same piece that we had for the length of a curve. We'll get this. And by summing all of these, we'll get an approximation for the surface area of this object. So one full frustrum, another frustrum, another one, until you get all the wrappers added up to give you the full surface area. And then what this will eventually become, and this is the note from before, as these get smaller, and again, I'm repeating myself, but if they get smaller and smaller, what we're going to get ultimately, we're going to say that k minus 1 and xk, they're basically the same. And if these are basically the same, then ck, which is between them, well, it's going to basically be the same as this or this. So this will become the integral from a to b of pi times 2f of x square root 1 plus f prime of x squared dx. And to write this a little, you say it, maybe a more familiar way. A to b 2 pi f of x square root 1 plus f prime of x squared dx. So this gives you the surface area for a surface generated by revolution or a revolving. Questions about that? Now there's another version of this too. You can also do the same thing for the y-axis. And there you go, about the y-axis. Questions about that? All right. So let's do an example. Now the derivation on this, I admit it might be a little hand wavy, but the idea that when the interval gets smaller and smaller, xk minus 1 and xk become practically the same, and that means since ck is between them, it's practically the same as that same x, or xk and xk minus 1. But it's a good way of remembering it. Hopefully that helps clarify some sense of why this could work. So let's do this. Find the surface area of the surface generated by revolving y equals 2 root x about the x axis. So what we're doing is this. And we have some limits for this. Let's say we're going to have x between 0 and 1 and 2. So this is our curve. There's 1. Pardon me, make this a little more scaled appropriately. It's not going to be drawn the scale, but we'll at least try to get the 1 and the 2 right. Somewhat right. So what we're going to do, we're going to take this, we're going to revolve it around the x-axis. To create this kind of a shape. It creates a shape sort of like this. And we want to find the surface area, at least of the wrapper of this shape, just the wrapper of it. Not concerned about the two bases. Let me see if I can. Draw that in a little bit more. But we just want the wrapper. Well, the way we're going to do this is we'll just use our formula. Now we need dy dx, or f prime of x. And our function was 2 square root x. And so that means we're going to get, if we do our derivative, we'll get 1 over square root of x. Now, we know that the function is y, which is our f of x, is 2 square root x. And we have our boundaries. A is going to be 1, and b is going to be 2. So what this is going to mean, the surface area, I'll abbreviate that SA, is A to B 2 pi f of x, or 2 pi y. You'll see it written that way too. Square root 1 plus f prime of x squared dx, which for us is going to be 1 to 2 pi times 2 square root x times the square root of 1 plus 1 over square root of x squared dx. So any questions so far? There's kind of a neat trick they use here when they simplify this, because this is going to look like when we do the integral, this is going to be one of those tricky integrals. But there's a really slick trick that they use that's kind of cool. So what we're going to get, 1 over 2, this will become 4 pi square root of x, everything outside the large square root. And then we've got this square root, it'll become 1 plus, we're going to square 1 over square root of x. That gives us 1 over x. And again, it's kind of like, wow, this is going to be kind of rough. We're to combine these into one term. Now, it still looks sort of like a desperate situation for our integral, but here's where they do a really kind of a neat thing. We'll bring the 4 pi out. 1 to 2 square root x. And what we can do is we can break up the square root. The square root of a quotient is the quotient of the square roots. And it's little tricks that are going to make our integral much easier. So those will cancel. And this is much more manageable. Here we can do a u substitution. So we let u equal x plus 1 That means du dx is equal to 1, or du equals dx. Then for the limits, so when x is equal to 1, then we'll have x plus 1 or 2, because u is going to be whatever x is plus 1. And then again, when x is 2, we have 2 plus 1 or 3. So we've got our u, we've got our du, we've got our limits. Let's do the integration. Any questions about that? All right. So this will give us 4 pi, the integral from 2 to 3, square root of u du. And that's going to come out to 4 pi times 2/3 u to the 3/2 from 2 to 3. Now, what's interesting in the textbook, I'm looking at this, they're actually going back to, they're not explicitly stating their u. I want to work with the u boundaries. What they did is they put it back in terms of x, and they use the x boundaries. So you could do it like this. You could call this 4 pi 2/3. We mentioned this briefly when we were looking at u substitution, but they're using this approach in the text. But they're using this, where you replace u with the x plus 1, and then you evaluate from 1 to 2. You could do that also. Either way would work. But since we went to the trouble of getting our u bounds, I'm going to stick with the u bounds. But you could do it this way, using the x bounds and replacing u with x plus 1. And so what this will give us, 8 pi over 3. We'll factor that out. U to the 3/2 from 2 to 3. Or 8 pi over 3. 3 to the 3/2 minus 2 to the 3/2. Or 8 pi over 3. And you're going to get 3 cubed. Again, another exercise in reviewing exponents. 2 cubed. We'll get something like that. Because the power to 1/2 is square root. And again, this is 8 pi over 3. Got the square root of 9 times 3 minus the square root of 4 times 2. And the square root of a product is the product of the square roots. We know what square root 9 is. That's 3. So we'll get 3 square root 3 minus 2 square root 2. And that's going to be the final answer. So we have pies, we have fractions, we have square roots. We've got it all in here. So questions about that? So that's going to be it for today. That's going to leave us 2 sections left. The section on work isn't very long. That's kind of a quick one. So we will do that one tomorrow. I'm sorry, on Wednesday. And then we'll take a look at moments of centers of mass, moments and centers of mass. And again, that's an important, it's the last section of the book, but it's a section where you have, it's going to come back. You're going to see it in Calc 3 again. So any questions about this?
Hello, Professor Coburn.
Yes.
So, I don't have any questions about everything for today. I think it's pretty straightforward.